In this video, we're going to continue on with covalent bonds. So previously we learned that the three types of bonds that we have are ionic bonds, covalent bonds, and hydrogen bonds. And where we left off with covalent bonds was this idea that within covalent bonds, there are two types. There are nonpolar covalent bonds and polar covalent bonds. And understanding of polar covalent bonds will naturally lead us to understanding of that third type, which are the hydrogen bonds. So let's talk about that. The learning objectives for this video are the difference between polar and nonpolar covalent bonds. And really that is the main thrust of it. So I would actually say that this is the most important part. Learning objective number 2 is pretty simple, just a definition. And number 3, this is pretty much just information. And then number 4, this is pretty important as well too, but there's not a lot of complexity to it. But number 1 is really the main thrust of the kind of cognitive stuff that you need to get down with this video. So when we look at sharing, we talked about sharing, and I used this image to you guys before, and I said that there's a difference between when an atom donates or gives away an electron, like somebody might give away an old pair of shoes, versus equal sharing of electrons. And this right here, when you donate electrons, that's when you form ions, right? Cations and anions and things like that. When you share, that's when you form these covalent bonds. And we looked at images like this where each atom could lay claim to having a completely full valence layer of electrons. Well, if you've ever shared stuff with people before, if you have a sibling, for example, an older or younger sibling, you know that sharing can occur, but it's not always equal sharing. So for example, I used this in a previous video to talk about equal sharing. So my brother and I played Hungry Hungry Hippos, and this game was equally both of ours. But then on the other hand, I actually had this, this is not a shot of the one that I had, but this is a remote control car that I got at some point, middle school or something like that. And we put this thing together, but my brother, it was an unequal sharing. So it was a car meant for the both of us, but really at any given point in time, if you looked, it's way more likely that he had his hands on the remote control than me. So technically we shared the car, but realistically it was an unequal sharing of this particular toy. So maybe you've had some experience with that kind of thing. Well, so similarly, here's what ends up happening is that there are some atoms on the periodic table. So there are some elements on the periodic table that tend to not play nicely with others. And so the most famous one that we're going to look at is actually oxygen, this one over here. But some of these, and there's no way for you to predict this, you just need to be told by a chemistry teacher, or in this case by me, that what ends up happening is that some of these atoms don't share nicely with one another. So what ends up happening is that once you start seeing a bond like this between oxygen and hydrogen, well, you already know. You can say, well, oxygen doesn't have a complete valence layer. He wants to have 8, he only has 2. Each of these hydrogen atoms has a single electron, and so oxygen may form a bond with 2 of these guys. So this oxygen formed a bond with hydrogen here and hydrogen over here. And so again, using the same language we did before, that when oxygen shares this one and hydrogen shares this one, they both fully lay claim to those electrons. They're technically sharing. If there's an auditor that comes through, then both of those electrons belong to both of those atoms, oxygen and hydrogen. However, oxygen is like the greedy big brother. And so what ends up happening is that if you look at this orbit here with hydrogen, see how it's a perfect circle? But once he forms a bond with oxygen, look at what happens. There's a little bit of a distortion. It becomes more oval-like. So what ends up happening is that this oxygen atom tends to hold these electrons more closely to it than hydrogen does. And so that atom, that property of holding on to those electrons a little more strongly, so I wrote up here, it pulls more strongly on the electrons, that property is known as electronegativity. So we describe oxygen as being an electronegative atom. Oxygen is a greedy big brother. Again, there's no way for you to predict that, but now I'm telling you now, so you should remember that forever. So oxygen is a greedy big brother. So you see that both those electrons have a greater chance of being closer to oxygen than to hydrogen. So here's what that leads to. It leads to the development of a partial charge, and that's what this symbol represents. So hydrogen is left with the partial positive charge, partial positive here on this hydrogen, and oxygen is left with a partial negative charge. Now, as a whole, the water molecule itself, this is a water molecule, is electrically neutral. It's just that parts of it are a little bit more negative and parts of it are a little bit more positive. But as a whole, it's not fair to say that it carries a full charge one way or another. And so when you look at this, then we describe this as being a polar covalent bond because there is a polarity here. There's a difference in charge, partial positive versus partial negative. Now, it's not really worth our while to say, well, what does partial mean? Does that mean it's a partial positive? Does that mean like 0.1? 0.2, 0.3. As far as I know, nobody has really quantified these things. We just say that it's a little bit positive here and a little bit negative here. And so again, the bond itself is a polar covalent bond. So then what is a nonpolar covalent bond? Okay, so now you know what a polar covalent bond is. What is a nonpolar covalent bond? A nonpolar covalent bond is actually all that stuff that I showed you earlier. I just didn't describe it as being nonpolar. What I will tell you, and you're just going to have to memorize this, is carbon. When you look at carbon and he forms bonds with hydrogen, carbon shares nicely. There is no distortion of that circle. See how that's a nice clean circle? It didn't get distorted into that oval-like shape. That's because carbon is not an electronegative atom. He does not have a tendency to pull more strongly on these shared electrons, whereas oxygen does. So carbon and hydrogen forms nonpolar covalent bonds. That's going to be really critical once we start talking about like biomolecules like lipids, for example, whereas oxygen and hydrogen form polar covalent bonds. Now, let's look at that then. So knowing now that that's a polar covalent bond, let's look at it again. Now we have this water molecule. The colors are different just because it's from a different textbook. So oxygen has a partial negative, hydrogen has a partial positive. Where we're at now is now we're going to talk about hydrogen bonds. Now that you know what polar versus nonpolar covalent bonds are, now then we can explain this other slide that I showed you previously saying, well, what the heck are hydrogen bonds? Hydrogen bonds result between molecules when there is a polar covalent bond. And so let me show you what that means. This thing over here between oxygen and hydrogen is a polar covalent bond. It is not a hydrogen bond. This is probably the most common mistake that students make. The most common mistake that students will make is to call this bond between oxygen and hydrogen a hydrogen bond. It's not. It's a polar covalent bond. So what is a hydrogen bond? It is when you see interaction between different molecules where there are charges, whether full charges or partial charges. So look at this one. These are partially charged atoms because of that polar covalent bond. And what we see here is the partial positive right over here interacts with the partial negative over here. Similarly, the partial negative of this molecule interacts with the partial positive of that molecule. The partial negative of this molecule interacts with the partial positive of this molecule as well as this one over here. And so we see that hydrogen bonds that are very weak. They're very weak and they're really transient. They don't just stay fixed like that. They're very brief, but they are super essential. Now, hydrogen bonds usually occur when hydrogen is bound to either any of these atoms, but the most common one that we're going to see in human physiology is this one right over here, when it binds to oxygen. So these then are hydrogen bonds. This is another depiction, H2O, right? 2 hydrogens and 1 oxygen. It's in your interest to freeze the video here and just take some time and look at that. And again, the main thing that students are going to confuse is if I were to ask you, describe the nature of the bond between oxygen atom and hydrogen atom within a single water molecule, you should say these are polar covalent bonds. But if I say to you, describe the interaction between oxygen atom and hydrogen atom of different water molecules, then you say, oh, those interact through hydrogen bonds. Now, those hydrogen bonds, oftentimes we can observe them. Well, I guess you're not really observing the bond itself. You're observing the result of the bond. If you look at the surface of water, there is a little bit of surface tension. And if you've ever taken a walk down the creek, you've seen little bugs kind of walking on water. If you could drop a little bit of water to a table in front of you, and if you dab it with your finger and bring your finger up north to the sky, you'll see that the water drags just a little bit. In other words, water molecules are attracted to water molecules. Now, the bonds are pretty easy to break, meaning that these bonds are strong enough to hold up a little bug like this, but if you put in like a tiny pebble, it's definitely not strong enough to hold that up. But nonetheless, these are important. This is just one more slide showing you, again, water molecules. Now, the difference here, what we're going to do is we're going to dump in salt. So this is sodium chloride. Sodium chloride we've seen already as being bound by ionic bonds. And I had said to you at that time, look, ionic bonds are strong, but they're pretty easy to break. You just add water. So what ends up happening is that when you dump salt in water, you already know what happens. At some point, you've put salt in water, and you know it dissolves very, very easily. Well, what does it mean to dissolve? It means that this crystal structure, or this crystalline structure of salt, sodium, and chloride, in this case, sodium is green and chloride ion is yellow. What ends up happening when you drop this in water, there's all these water molecules all over the place, and each sodium ion gets surrounded by water, and each chloride ion gets surrounded by water. But if you pay attention to details here, here's what you'll see. Recall that sodium is a positively charged cation. Therefore, when he gets surrounded by water, it's really going to be those partial negative charges on the water molecule that surround sodium. On the other hand, chloride ion is a negatively charged anion, so when you drop him in water, what you're going to see is the partial positive charges of the hydrogen atoms within the oxygen molecule surrounding the chloride ion. So this is a so-called hydrated sodium ion and a hydrated chloride ion. In other words, basically this is salt that's now dissolved in water. So check your knowledge. You should probably freeze the video and try to answer these questions. Ionic bonds are formed when one atom donates an electron, therefore becoming a positively charged cation, and another atom receives an electron, therefore becoming a negatively charged anion. Now, the cation and anion hook up together because they have opposite charges. That's an ionic bond. Covalent bonds are formed when two atoms share electrons, and those two types are polar and nonpolar covalent bonds. And hydrogen bonds are formed when you have a non-polar, I said that completely wrong. Hydrogen bonds are formed when you have a polar covalent bond, and partial charges then interact with other molecules that have charge to them. So everything here there's nothing new here. It talks about ionic bonds, it talks about polar covalent bonds, and it talks about non-polar covalent bonds. So take some time to look at that slide. What I want to do now is just kind of wrap things up. And it looks like there's 3 more learning objectives, but they're pretty straightforward, so I'm going to go ahead and go through them here in this video. The first thing is, and these are kind of miscellaneous, meaning that they don't fit nicely into talking about chemical bonds and that kind of stuff. So these are kind of 3 miscellaneous concepts that I'm going to throw in and tack on here. Okay, the first is a free radical. You may have heard of free radicals. Free radicals realistically are just atoms or molecules. They're atoms or molecules with unpaired electrons in their valence shells. So that is kind of a very common definition of it. Now you might be saying to yourself, unpaired electrons, wait, what does that mean? There's more to it, but for our purposes, for what we do in Bio 141 and Bio 142, we're just going to say we really mean an atom or molecule where there is an unfulfilled octet rule. If you have an unfulfilled octet rule, that atom or molecule is going to just do whatever it takes to end up satisfying that itch. And in doing so, what ends up happening is if he can't find kind of a reasonable negotiation with another atom to satisfy that octet rule, he's then just going to go on and start stealing stuff. So anyway, those are free radicals. Free radicals are commonly formed. We'll see some when we do energy metabolism, but generally speaking, in your body, we have built-in antioxidant systems to neutralize them. And I'm going to talk about those words oxidation and reduction a little bit later on. But we have these things called antioxidants you can get from your food, of course, but we also have intrinsic systems, and those are meant to neutralize free radicals. Okay. The next thing, another miscellaneous concept, how chemical formulas are written. We generally speaking, just like a lot of equations, we read this left to right. And so the reactants are traditionally on the left side of the equation. Reactants basically means the players. If you think of like 2 plus 2 equals 4, for example, 2 plus 2 would be the reactants. Those are the things that are interacting. In the yield, the thing that you get on the opposite as a result of the chemistry is considered a product. And so reactants and products. As you go into chemistry, we're not going to do so much of it here in this class. We'll see maybe 1 or 2 examples down the road, is that you can see that sometimes arrows point just in one direction. Sometimes it's a bidirectional arrow because they are reversible chemical reactions. And the last miscellaneous concept, but really, really important, is this idea of pH. pH stands for power of hydrogen, and that is an indicator of acidity. By definition, an acid is something out there that donates hydrogen ions to a solution. That's what an acid is. A base is something that donates hydroxide ions, OH over here, to a solution. And a salt is just when a cation and anion get together and they separate out in solution. So like sodium chloride is your probably most famous salt. So this idea of acidity becomes really important, and we have a scale to measure acidity. And the pH scale, the power of hydrogen scale, traditionally goes from 0 to 14. And at 7, the number of free-floating hydrogen ions is exactly balanced by the number of free-floating hydroxide ions, and then this thing is considered to be neutral. So 7 is neutral. As you go down the pH scale, 6, 5, 4, 3, 2, 1, you get increasingly acidic. As you go higher up on the pH scale, you become increasingly basic or alkaline. Now, just to be clear, acid being really, really acidic is really, really bad. It'll kill you. Being really alkaline is really bad. It'll kill you. If you drink an acidic solution, it'll kill you. You drink an alkaline solution, it'll kill you. Common examples of things that are, so again, let's take neutral. This is your pH scale again. This is the pH scale getting more and more acidic as we go higher. As we go lower on this depiction anyway, we become increasingly alkaline. So distilled water has a pH of 7. As you go down, you get more and more acidic. So your stomach acid is about pH 2. Bleach is pH 12. Both of them are really, really nasty and really, really toxic. So our pH, and this is a number you're just going to have to memorize. Your blood pH is 7.4. Most people will give you a range of like 7.2 to 7.4. So what I want you to know is that you are ever so slightly alkaline. Okay, our body is ever so slightly alkaline. We'll talk a little bit more about pH when it becomes more directly relevant and how pH will mess us up. But what you need to understand for right now is that this is the pH scale. It's a measure of acidity with lower numbers indicating greater acidity and higher numbers representing increasing basic environments. So that is your pH scale. All right, to recap. The difference between polar and non-polar covalent bonds we've covered. We've basically identified a free radical. It's something, atom or molecule, with an unsatisfied octet rule, and therefore he's resulted to stealing electrons from other molecules, destabilizing them as a result. In a chemical reaction, reactants are the things that are interacting with one another in chemistry, and products are the things then that are formed. And the pH scale, neutral pH is 7, our blood pH is 7.4, therefore it is ever so slightly alkaline or ever so slightly basic. And that'll wrap it up for this video.